Yeah, because we need to refresh our memory a little bit. All right. So our goal, we want to sort a given array, but we use a different property. Yeah. Our main focus is on the order of the elements. Yeah, we want to study the order of the elements. But in which way to study? Yeah. Because when you study, you need to choose some feasible way to study. Yeah. So we compare two elements. Yeah. Every time when we apply one comparison, we apply it only on two elements. Yeah. And when you do one comparison, here we also assume, yeah, last time I mentioned a little bit, we can, at this point, we can assume the distinct, our elements distinct, yeah, for convenience. Yeah. Because later, after we find the solution, we can easily make adjustment to remove this assumption. All right, so here, let's assume all the elements are distinct. Yeah. Then, when we do comparison, we only have two possible outcomes, greater than, less than. Yeah. First element, second element, or the general case. This is the general case. Okay? General case, when we do comparison, A sub I and A sub j, there are only two possible outcomes. The first element is less than the second element, or the first element is greater than the second element. Yeah. If the first element less than the second element, yeah, here the first element we assume the subscript I is less than j. So here you can see we pay attention to all the details. This kind of details important. Yeah. So we assume I subscript less than j subscript because we want to control, resolve the uncertainties. Yeah. Because when we study data, a lot of uncertainties. You need to find a way to reduce the uncertainty. In problem solving, you need to do a lot of work to reduce uncertainty. Here, we reduce uncertainty. Make subscript I less than subscript j. Then, if the value of the first element is less than the value of the second element, then these two elements, we only look at these two elements. We can forget all other elements. So between these two elements, the order between these two elements is the same as the one in the final ordered array, right? Final sorted array. Yeah? Final sorted array, the order between these two elements must be in ascending order, right? Yeah? So here you can see, if the first element is less than the second element, that's the desired state we want to have, right? Yeah, desired state. That's what we want to have. Yeah. That means we should not do anything between these two elements. Yeah, because they are in the right state. We should keep the right state, right? Yeah, we should not change the right state. Yeah. But the other case, if the first element, the value of the first element is greater than the value of the second element, then that state is not quite right, because they are in the opposite order. If we compare it in our destination situation, the whole array, when the whole array is sorted, then the order between those two elements not right, right? not right with the current state. Yeah. So with that observation, when we need to spend our time to do the work, which state we should focus on? Ascending order or descending order? Yeah. Ascending order, right order. Descending order, wrong order, right? Yeah. So we should focus on the wrong order. Because for the wrong order, we need to fix it. We need to do some work to fix it. For the right order, do nothing. Do nothing. Keep it, right? For the right order, we should keep it. The wrong order, we should fix it. Yeah. So our energy and our resource should be allocated to the wrong order case. Yeah. So for that reason, we introduced this important concept. Yeah. Why we introduced this concept? Inversion concept. Because that's the main state we want to study. This inversion, that's the reason that causes the whole array not sorted. That's the whole reason. Yeah. And yeah, so this critical property we discussed the last time. Yeah, this critical property, yeah, last time, you can see, yeah, basically, if the array is not sorted, the main reason is there exists at least one inversion. How about that? There exists one inversion. That's the reason the whole array is not sorted. Think about, given an array, if there is no inversion, in a given array, no inversion, how good it is. Yeah? No work, right? No comparison, no sorting work. You need to do nothing. If there is no inversion, that's already our goal. We achieved the goal already. No inversion. Now, here you can see, for this, our second sort, the main property we want to explore is on the inversion property. Think about it. That's the key property we want to explore. Yeah. So if you have this understanding at this step, so you can easily make your plan. What is our plan to sort this array? Reduce the number of inversions. How about that? Because the total number of inversions, there is a certain number there, right? How many inversions in the given array? There must be some certain number. But can you do something to reduce the number of inversions again and again? Keep doing that reduction work. Eventually, you reduce the number of inversion to none. Then you sort it. You sort the whole array. How about that? This point of view? Yeah, it's different from our previous selection sort point of view, right? Yeah. So here you can see, when we change our view, we also change our algorithm. Yeah. So here you get the idea. We change our view. Yeah. Yeah. If we look at the same problem using a different view, yeah, we may have many different algorithms. Yeah. All right. Yeah. Now, let's based on this analysis. Yeah. Here, we just try to rewrite this statement in different ways. Yeah. The first way, if the array is not sorted, there must be an inversion. Yeah. So that's in our discussion. Yeah. We observe the statement. Yeah. There must be at least one inversion. Yeah. Not sorted. All right? Yeah. To see it, yeah. So here I review. Remember last time in this first statement, we look at the last time, the first, the first statement, this one. We use the contrapositive method to prove it, right? So I reviewed the contrapositive method last time. So this second statement, let's practice that contrapositive method another time. A little bit, practice. How to see this statement is correct? Let's apply the contrapositive method. And see, we negate conclusion. The second part of the sentence is the conclusion, right? There must be an inversion. That's the conclusion. Now we need to negate it. That means we need to write a sentence on top of the fact that this is wrong. Okay? There must be one inversion. This one is wrong. So we need to write a sentence to mean this conclusion is wrong. What's that? No inversion, right? Because there must be one inversion is wrong. What sentence make one inversion is wrong? Zero inversion, right? Zero inversion make it wrong. Two inversion does not make it wrong, right? Because two inversion contains one inversion, right? So the only way to make it wrong, there is no inversion. So that's the way we negate it. That's the NC, negate this conclusion part. So if there is no inversion, what can you get? Given array, there is no inversion. Can you see the whole array must be sorted? Can you see it, right? Must be, because you just compare two adjacent elements, right? All the way from beginning to the end, you're going up. When you compare two adjacent, you're always going up, right? From the first element to last element, moving up. That means ascending, the ascending order, right? So you get a statement that is the whole array is sorted. You get that statement. But look at the hypothesis, the first part of the sentence, hypothesis. The array is not sorted. Do you get a contradiction? So when you get a contradiction, so your contrapositive method, based on your contrapositive method, the negation step of the conclusion part is wrong. Why you get a contradiction? Because your first step, you do the negation. That is wrong. If that is wrong, then the conclusion, original conclusion, statement is correct, right? Because when you do negation, it's wrong. So you cannot do negation. Then the original statement must be correct. So that's our, practice our contrapositive method. All right? A simple example. So then we write it another way. These two ways actually equivalent. So although we use different way to write, but we treat them same, meaning the same. What's that? If the array is sorted, it's not sorted. Same hypothesis, but we modify the conclusion slightly. There must be an adjacent inversion. So here we just add one word, an adjacent inversion. But they are equivalent. Can you see it? We add an adjacent word to improve the previous statement. Previous statement is correct, but still, if we want to apply it in our algorithm, still not quite convenient. That's the problem. Not quite convenient. Now, we want to improve the version on the previous statement to make it more convenient for our algorithm development. That's the goal. Okay? All right. So we added this adjacent, important adjacent word in front of this inversion. Yeah. Yeah. To see it's correct, also very important, right? Yeah. We use the same contrapositive way. Okay? Here, I need to do it quickly. Okay? Negate the conclusion if there is no adjacent inversion. No adjacent inversion. Zero adjacent inversion. When you consider every adjacent pair of elements, they are in ascending order. Then you can easily see the whole array must be in ascending order. Yeah. That's so easy. Yeah. So another contrapositive application. Yeah. All right. But why the third statement is better than the second statement? Yeah. Here, that's another important point I want to convey here. Yeah. Because first statement, we didn't mention what kind of inversion, right? Arbitrary inversion. No. So we talk about arbitrary inversion. Arbitrary inversion, that means the inversion we are talking about here is a global inversion. A global inversion. Okay? Yeah. But the third statement of the adjacent, it's not global inversion. Okay? So the change we made is very important. We changed from global view to local view. That change is important. Okay? So here I give you another general way used in problem solving. In general way, when you do the global work, it's much harder. Yeah, because your data, think about it, you have large amount of data. When you need to do something covering the global data, much harder. But when you only target a small portion of the data, local portion, it's much easier. Yeah. Yeah. So this is a common understanding in problem solving. Yeah. Yeah. If we, here I recall the greedy algorithm a little bit. Greedy algorithm, each step we find the best solution at each step. That's a local way, right? Yeah. Yeah. We do not look at the problem globally to find the best solution. We only try to get the best we can get in a small portion of the data. That's the greedy algorithm. Yeah, much easier. The global way, optimal, too hard. Yeah. All right, so this is another important view in problem solving. Now we get this local view on the inversion. Yeah. So the statement, the importance of statement number 3. Yeah. Yeah, here, and write the number. The importance of this statement number 3 is you only need to remove all the adjacent inversions. Then it is guaranteed the whole array is sorted. How about that? This is our current view. Yeah. So we change our objective. Now our objective becomes we need to remove all the adjacent inversions. Then it is guaranteed the whole array must be sorted. Yeah, because by third statement, it tells us that. You do not need to working on the global inversions. If you base on the second statement, you you may need to work on the global inversions, right? Then too much work. Yeah. Let me ask you, how many global inversions? Yeah, before we continue, yeah, here, I just ask you, yeah, how many global inversions? Yeah, given n elements, the number of yeah, so we know data size is n, right? Yeah, data size equals n. Now, first I want to ask you the number of, maximum. Yeah, here we talk about maximum, okay? Yeah, yeah, because maximum number of global inversions. Oh. Can you get that? That number equals maximum number of global inversions. How many? Global. All right? Can you see it? The same number as the total number of pairs. How many pairs? Remember? Number of pairs. Remember last time I used the combinatorial number. N choose 2, right? N choose 2, that's the number of pairs. Remember we did before. N choose 2. All right? The maximum number corresponds to the case. For any pair, you get one inversion. Any pair, the worst case, you get one inversion. Yeah? So the maximum number of inversions is the same as the number of pairs. Okay? So this number, all right? This number, all right? That's the first number. Second number, if I ask you, the number of adjacent inversions, how many? Now, the second number is the number of, I added this word, adjacent. Inversions, that number. Can you see the maximum number of adjacent inversions? Only adjacent. Adjacent pairs. Consider the number of adjacent pairs. Each adjacent pair corresponds to one inversion. What's that number? Maximum number of adjacent pairs. AJ, the first time you said that is correct. That's adjacent. N minus 1. Yeah. So this number is N minus 1. All right? Yeah? So you compare these two numbers. Yeah. The first number is much larger than the second number, right? Much larger. If you're setting your objective to reduce the much larger number, is it harder? So based on the third statement, our objective we set reduce the smaller number. If you base on the second statement, you need to reduce the first larger inversion number. Which one is easy? Which one is harder? Right? Yeah. So it's a no-brainer, right? Yeah. We should do the, adjacent way. Yeah. Adjacent way. Yeah. So that's our. So with this kind of understanding, you can work on the, our second sort. Yeah. Now we are ready to write our second sort. Yeah. All right. Yeah. Okay. Yeah. So here, yeah. So yeah, a little messy. Here I wrote, from this analysis we have this. Yeah. From global view to local view. Okay. Yeah. So we change our second statement is the global view. Our third statement is local view. Yeah. All right. Now, next question. How to fix an adjacent inversion? Suppose you find it, you detect one adjacent inversion, but how to remove it? You need to solve this technical problem. Then you're almost there. Almost there. How to fix one adjacent inversion? Yeah. The first element is greater than the second element. Yeah. The order is not right. You want to fix it. You want to fix the order between these two elements. Swap operation. Simple swap. Fix it. Simple swap. So fix it. Okay? Yeah. So next, we will do swap operation. Whenever we detect one inversion, we swap two elements in this inversion. Then inversion is gone. Right? Then another detection of inversion, another swap, and so on. Then eventually we will get the whole array sorted. That's the idea. All right? Yeah. So let me complete implementation idea. All right. Remove all the local inversions by local swaps. So this local is the most local way adjacent, right? Yeah, adjacent. Adjacent, is the most possible local way we can think of. Yeah. All right. Yeah. Yeah. So let's look at the basic procedure of this whole implementation method. Step 1. Start from the first element for each scan. So we scan the whole array. Yeah. But starting point, every time when we do a new scan, we always start from the first element. Yeah. The last element in this first step, we cannot see it. What is the end point? We don't know. Yeah. But it tells us the starting point always the first element for each scan. Okay? All right. Then second step, do swaps one by one from left to right when necessary, right? Yeah. So here, yeah, because sometimes you do not need to do swap. Yeah. Because when you check two of the adjacent elements, they are in order, no swap. Yeah. So this step, you need to add when necessary. Yeah. If necessary, then you do swap. Yeah. If not necessary, next checking. Next inversion checking. Yeah. That's the second step. All right. Then the third step. Start at the first in-place element. Yeah. So to understand the third step, then we need to understand a little more here. Yeah. Yeah. Because think about here, let's consider our first scan. Yeah. Our first scan, after the first scan, yeah, from beginning to end. Yeah. Which element is in place? Can you see? Is there after the first scan from beginning to end? Okay? The scan means you do an adjacent comparison. If you get one inversion, you swap two elements. Okay? Yeah. You do all the way from beginning to end. So after this whole scan, can you see any element in place? Any element in place? Yeah, because it's important. Any element in place? Use your intuition to imagine, the change of your data from beginning to end. Because every time you check the first two elements, after the swap, the larger one will be at the second position, right? Next time you compare another two adjacent elements, the larger one always move to the later position, right? Yeah. You do all the way from beginning to end. What can you see from beginning to end? Yeah. Yeah. Look at the location of the maximum. Look at the location of the maximum. Yeah. Right? The last element. Yeah. So, yeah, not first. Yeah. Yes, yes, yes. So the last element is in place. After first scan, last element in place. Okay? But only the last element in place, that is guaranteed. All other elements, it's not guaranteed if they are in place or not, right? They're not guaranteed. All possible. Okay. But the last element is guaranteed to be in place. All right? That means you need to do another scan, right? Yeah. But when you do the second scan, we do not need to touch the last element, right? Already in place, why you touch it? No. So we need to eliminate the last element. Okay? In our second scan. Okay? Our second scan, then the second last element in place, right? Second last element in place. And so on. Third scan, the third largest element in place, and so on. Okay? Yeah. Yeah. So based on that observation, so when you do your new round of scan, stop at the first in-place element. Yeah. And in-place, when you hit an in-place element, stop it. Yeah. Okay? Don't waste your work. Yeah. Comparison, swap work. Don't waste it. No. Yeah. So when you set a boundary, okay? You set a boundary. Yeah. Separating the elements that are in place and not in place. All right. So based on these three steps, you can complete the whole sort algorithm. Yeah. So this algorithm, yeah, based on the the property, main property, yeah. So we only do adjacent inversion checking. We only do adjacent inversion checking. So that phenomenon, yeah. So here, that kind of phenomenon, yeah. Yeah. Later, people call it bubble sort. That's the bubble sort. Yeah. All right. Yeah. All right. So here, let's do summary a little bit. Yeah. Every scan, there is one element in place. Yeah. That's the property. The in-place element of each scan appears at the end of the current array. Yeah. Okay. Location of the in-place element. The current array is a subarray that excludes all the in-place elements. Yeah. Yeah. So this kind of details. So when you write your implementation code, yeah, so you need to pay attention to, this kind of details. Yeah. Yeah. So then you can write a code. Yeah. All right. Yeah. So then visual imagination. Yeah. Yeah. Because in your mind, you need to use your intuition to visually understand, the whole sorting procedure. Yeah. Swap looks like a bubble moving to the right. Yeah. So that's the bubble sort. Yeah. All right. That's our second sort. Yeah. All right. For the second sort, yeah, we can also do efficiency analysis, but the same as the efficiency analysis of selection sort. That means you only have one case. No matter what kind of input you get, yeah, the input you get It could be the whole array already sorted, right? If the whole array is sorted, can we do better? If the whole array already sorted, yeah. So, but for this question, when we, so let me repeat this question again. So this question actually, there is some hole there. There is some hole. So if the input we get is an ordered array, if we apply the bubble sort, can we do better? So this question, because a little, not very precise. Because the meaning, the reason is, in which sense you mean better, right? Because when we say better, can you describe what do you mean better, right? Because there are two different ways of understanding. If you include swaps, well, when you talk about better or not, if you include number of swaps, yes, we can do better. Because no swap, right? But in the bubble sort, the swap is not a basic operation. Remember, the basic operation is the comparison. Comparison in the bubble sort, more important. Because we always, when we do the checking, we always need to do comparison. But swap, sometimes we do, sometimes we do not do swap. So comparison operation is the basic operations. If your better means, when you say better, you target the number of comparisons, then the answer is no, you cannot improve. If we count the number of comparisons, for any input, we need to do the same number of comparisons. Can you see that same number of comparisons? This number. We need to do this number. Right. Because there are many scans, right? When you count the number of comparisons, how many comparisons in the first scan? n-1, right? How many comparisons in the second scan? n-2, and n-3, and so on. The last scan, one comparison. So you add all these numbers up, so you get that number. Okay? So for any input, the number of comparisons for the bubble sort always this number. You cannot reduce. Only one case. When you count basic operations, only one case, that number. So from this point of view, the same as the selection sort. One case. So the best case is this one, the worst case is this one, the average case also this number. One case. All right, So that's the basic operation, comparison, not swap. Right. All right, so after this, so we complete, I may just use 5 minutes to complete part A, because that topic, there is some, similar view to this one, so we look at that. All right. So then we can start part C a little bit. All right. Get out. So part A, last page. Last page, we're halfway. So let me recall a little bit. So we did comparison. Method 2, method 1, right? Yeah. So I ask you which method is better, right? Yeah. So here, I need to change my pen color a little bit. Right. Yeah. So here, yeah. Our conclusion. Yeah. So we did a lot of comparison. Okay. Yeah. Yeah. So our second method, this growth function. Remember, this growth function grows slower than the growth function of growth function. We only use square. Okay. We don't use 1/2. Okay. Grows slower than the growth function of the first method. So that means our second method is faster. All right. Yeah. But here I want to make some comments. Yeah. So we almost finish it, but just a few more comments. Yeah. Observation. Yeah. A few more comments on this. Yeah. Why our second method can be better than the first method? Yeah. First method, the main difference. Yeah. Let me recall the main difference. First method, we do not do sorting. Okay. Yeah. We just do the comparison directly. That's our first method. No sorting. Our second method, before we do uniqueness checking, yeah, the problem is checking for if the given array, the elements in the given array are unique or not. Yeah. So that's the problem. Yeah. All right. But the second method, before the checking, we sort the whole array first. Yeah. We sort the whole array using n log n. Yeah. This many comparisons. Yeah. All right. So here, and we treat this step. We organize the data, right? So this step we organize our data first before we do our real work. Yeah. Yeah. So that step, we need to use our resource, a lot of resource. That step we treat as the investment. Yeah. Because after this data organizing step, we can enjoy the benefit of the organized data, because our data becomes organized. Yeah. If we do not do this step, our data not organized. Yeah, very, randomly distributed. Yeah. So when we work on that kind of messy data, we need to do more work. Yeah. The second way, we only need to work on well-organized data, so we do much less work. Okay? All right. How much less? Now, that's the comments I want to compare it with our bubble sort. Yeah. Remember, our bubble sort, yeah, the reason we can, do the best we can, because we change the global view to local view, right? Yeah. Yeah. We change the global inversion to local inversion. Yeah, that's the reason. Yeah, we can solve that problem. Here, another global view to local view example. Okay? Yeah. Yeah. Because in method 1, if you do not sort the whole array, when you do element uniqueness checking, you need to do global comparison, right? Yeah, global comparison. Okay? Yeah, that is hard. Yeah, too much work. Yeah. But after the sorting, you do not need to do global comparison anymore, right? So you only need to do adjacent comparison. See? When we do comparison, we only need to compare 2 adjacent elements. Yeah? Because the whole array is sorted. Okay? If we want to check if 2 elements are the same, you only need to compare adjacent elements. Okay? Yeah? So that's another changing from global view to local view example. Okay? Yeah? So you can improve your algorithm by this kind of methodology. Okay? Yeah? From global to local. Okay? Yeah? So that's the point I want to convey here. Yeah? These two examples all reflect this important point. Yeah. All right, then I can, finish this part A also. Yeah. Just this last comment. Yeah. All right, now we move to part C. Part C, the last part of Module 2. Module 2, we only have 3 parts, A, B, C. Yeah, but this part is more important. Part A, Part B, we do preparation for Part C. Yeah. Part C is our core part of Module 2. Yeah. So we need 2 classes. So today we have just 15 minutes. Yeah. So today we start a little bit, and next time we may not be able to complete. Yeah, but we need another 10 to 20 minutes after next class. Yeah, but when we start Module 3, we use 10 to 20 minutes to complete this Part C, the remaining part. Yeah. All right. So today let's. Sorry. Part C, asymptotic notations. Yeah. Yeah. Also a very abstract topic. Yeah. But it is extremely important for this algorithm class. Yeah. Because after this topic, we will always use asymptotic notations to describe the efficiency of all our algorithms. Yeah. All right. C.1, Introduction to Asymptotic Notations. Yeah. All right. Let us look at the limits of 2 growth functions. Yeah. So when we compare 2 growth functions for 2 algorithms. Yeah. So usually we use the limit to compare. Yeah. So the ratio of 2 growth functions to compare. So when we do that, we want to see how many possibilities, the limit of this ratio of 2 growth functions, how many cases do we have when we look at the ratio of 2 growth functions? Yeah. 1, 2, 3, 4. Okay. These 4 cases. All right. The first case, the limit equals 0. Yeah, the limit equals 0. Okay. The second case, non-zero constant C. Yeah. Yeah. So non-zero constant C, but I like to make it positive C. Positive constant C. Yeah. Why? Because our 2 growth functions are supposed to be positive functions. Yeah, the value. Yeah, because our efficiency function, we count the number of basic operations. So that counting number should be positive. Yeah. So our C can only be a positive number. Yeah. Positive constant. Then the third case, infinity. The ratio of these 2, infinity. Yeah. The last case, other than these 3 cases, there is a last case. Last case. The last case is the limit does not exist. Yeah. That's different. Okay? Different from the first 3 cases. Yeah. So this other here, mainly it means the limit does not exist. Okay? Yeah? That's possible. Limit does not exist. Okay? Yeah? Yeah. All right. So, yeah. All right. So let's look at these 4 cases one by one. Yeah. All right. Yeah. Yeah. No limit. All right. The limit does not exist. Yeah. Limit has a definition, right? The definition of the limit does not follow. Yeah. So you will check that definition. No, doesn't work. Okay. Yeah. But to see that, yeah, because this part for most students, it's not easy to see. Yeah. For this part. Yeah. So, but here I can give you some simple example to let you see. So under what situation limit does not exist? Yeah. All right. Consider this limit. Yeah. For the first f function, so let's think about n squared plus 1 times all right, 3 minus -1 to the n. Okay? All right, so this is the f function. G function, n squared minus 1, 4 plus. Can you see? Now we want to see if the limit of this ratio exists or not. All right? We want to see. Yeah. 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 So not infinity. Yeah. You know. Yeah. Infinity case. Yeah. It's a special case. Yeah. Although infinity case, we do not treat the limit exists. Yeah. Infinity, there is a special case. So we single it out. Yeah. So that's always we single the infinity case out. Yeah. But this does not exist, does not belong to the infinity case. Okay? All right. In this example, yeah. First, n squared plus 1, n squared minus 1, can we cancel out? Yeah, because plus 1, minus 1 difference is so small. All right? Yeah. Because if you do not feel comfortable, because cancellation you do not feel comfortable, right? But if I write one more step, you will feel comfortable. I just write one more step. Can we divide it, numerator, denominator, both by n squared? Right? Divided by n squared, we can do it, right? Yeah. So 1 plus 1 over n squared times something. So 1 minus 1 over n squared, something. Okay? All right. After this division by n squared, now do you feel more comfortable to cancel out when n goes to infinity? Yeah? 1 over n squared, the limit is 0, right? Yeah? So now you will feel much better, you know, it can be canceled out. By after taking the limit, okay? After the limit, they are gone, okay? Those two factors, they are gone, okay? All right, then that means we only need to focus on the remaining part, right? Yeah? When we take the ratio, we do not need to look at this, you know, n squared part. We only need to look at the remaining part. Yeah. All right, what's the remaining part? What's the remaining part? Yeah. Let us try even odd number, okay? Yeah? Because they take two values alternatively, even odd, based on n even and odd, okay? All right. When we start n even, n 0, that's even, right? Yeah. So even 3 minus 1, it's 2, right? And 4 plus, that's 5, okay? Yeah, so the first number should be 2/5. The second number, A is odd. 3 minus -1 is 4, okay? All right. 4 plus -1, it's 3, right? So the second one is 4/3. Then another even number come back, that's 2/5 back, and 4. Here you can see in this pattern, these two fractions appear alternatively in the sequence. Okay? The first number, second number. When you look at the sequence, does it exist a limit? Is there a limit? No limit. Okay? Up and down fluctuation, right? Never converge. When we say limit, it must converge to a number, right? That means there is a limit. Convergence. Yeah. But this diverge. This sequence diverges. Between yeah, oscillation, no limit. Okay? Yeah, because limit, yeah, so.
Isn't it somewhat like a limit though? It's just a limit in that specific sequence system, right? The sequence system says it will never go outside of 2/5 the fourth.
The limit means the sequence must converge.
So, okay, so
Converge to one number.
Okay, so
Yeah.
and this way that we're defining limit means it has to converge.
Yeah, yeah,
Okay.
yeah. Yeah. All right. Yeah, so no limit. That's our case number 4, other. All right. That's the other case. All right. No limit. All right. Yeah. So then, these 4 cases. Order, yeah. So here, we introduce a concept called order of growth. Yeah. Because we want to compare these two growth functions. Which one grows faster? Which one grows slower? Yeah. So in our discussion, we like to use a concept called order of growth to do the comparison. The one that grows faster should have higher order. Okay? The one that grows slower should have lower order, things like that. Yeah. But what's the definition of order growth? At this point, it is still a little vague, yeah, because hard to say it clearly at this point. Yeah. So later I try to describe this concept, order of growth concept. Yeah. All right. Here, from the first case, the limit of the ratio equals 0. That means, yeah, so you just imagine in the comparison, yeah, the denominator function dominates the numerator function. Yeah. So definitely the denominator function grows much faster than the numerator function, right? So if we use the order of growth concept, we should say the order of growth of the g function is greater than order of growth of f function. That's the first case. Yeah. Second case, the order of growth this time, because it's a non-positive constant, the ratio, positive constant, okay? Yeah, yeah. Although this c could be a large number, small number, you know, any positive number is possible, but if you look at the trend of the growth, on the same trend, right? Yeah. Scale is different because c control the scale, up or down control the scale. But the shape, the growing shape trend, pretty much the same. Okay? Yeah. The scale is different. Okay? Yeah. All right. So in this case, we can say they have the same order of growth. Okay? Yeah. Then number 3, yeah. Number 3, yeah. Just the opposite of case 1. Yeah. So that's like flip, right? Yeah. Opposite of case 1. So order of growth of f function is greater than other growth of g function. Okay. Case 4, unknown. Well, case 4, limit does not exist. What should we do on case 4? No limit. That means this method is useless for this case. So we should find a different method. So for case 4, in order to study case 4, we cannot rely on the limit method. It does not exist. So we need to find a non-limit method to study case 4. So we can do it. We can do it. Non-limit method for case 4. All right. So let me stop right here. So next time we will complete the remaining part. At least the definition of the asymptotic notations. For examples, we can do first a few, but the main part of the example we will leave to next week. But this week, the end of this week, I need to assign homework assignment number 1. This week, okay? Our big assignment. Because at the end of this week, we complete 2 modules. So we have plenty of material to cover in this homework assignment. All right? That's it.